Okay, yeah. So, okay, just a show of hands, like how many of you have worked with C++ before? Okay, and how many of you are like completely beginner to C++, just so I can tune my difficulty? Okay, sure. So I'm going to sit down for this because kind of tired, but yeah, so static reflection. Okay, so here's the agenda for today. I'm going to talk about like briefly what is static reflection and then why we want to use it. And I'm also going to compare it to some other languages, but I think most of the talk today will be example driven. So I'll go through like a few examples from the C++ static reflection proposal. And yeah, I'll basically go through the examples and try to explain them. So let me bring up my notes. Yeah, so what is reflection? Roughly speaking, is when a program can kind of modify itself. So when I first started learning programming, I asked my dad, can a string be a variable name? And he said no. And it turns out at the time he answered me, the answer was no. But like shortly after ECMAScript 2015, which is ES6, had started supporting runtime reflection with object.keys. So yeah, so yeah, nowadays a string can be a variable name, meaning that you can say like the value of this string is my variable name, and that's quite a powerful language feature. And so informally, reflection in general means that a language can modify itself. And if you think about it from a very like primitive point of view, if let's say you're coding in assembly, reflection is actually ignoring like all the read-write permissioning and all that. You're coding assembly. Reflection is quite trivial because assembly can just like read the contents of an address and like modify it. So assembly kind of comes with the assembly is very easy. It's very easy to implement like reflection in assembly, right? Because it's just bytecode all the way. And if you see interpreted languages on the other hand, it's also very easy to implement reflection in interpreted languages because you can just put it in the interpreter. You can just say the interpreter set the name of the variable to be something. And the challenge comes with compiled languages because if you want to let the source code like modify itself with compiled languages, you kind of need to bake it into a compiler because the compiler takes like source code, like C++ code, and turns it into assembly. And then now, if you want runtime reflection, for example, now your assembly kind of needs to know what the original source code is, and that can be difficult. So yeah, so that's reflection in general. There's runtime reflection and static reflection, and static reflection refers to the ability to do this during compile time only. So some languages support runtime reflection like JavaScript and Python, and some languages only support compile time reflection. So I'll be talking about C++, which supports compile time reflection, or rather is going to support static reflection in 26. And when you talk about reflection, there's also reflection over various like entities. Like there's reflection over fields, methods, types, annotations, and code, and so on. And I would say like since quite early in C++, you can already have like very minimal runtime reflection. Like you can print like runtime type information. That's kind of like a type of reflection, but only in 26 can you kind of have more reflection over a lot more things. And yeah, and reflection over code is also very powerful, which is like Java is actually like working to support with a project that's upcoming. So application of reflection, I think the most common one is, okay, there's a lot of applications of reflection, but the most common ones would be like ORMs. So if you work with a DB, you know that you talk to the DB over SQL, and it's bad practice to write like raw SQL queries in your code because when things change, when the DB schema migrates, then you have a lot of maintenance issues. So one way would be to work through a library called an ORM, and basically it's like it kind of maps each table to like some kind of class or struct, and instead of modifying the raw query directly, you modify the fields and then you do some kind of like commitment through the library. And reflection is one of the features you need if you want to write like a ORM, and specifically if you want to write it neatly. Like you want to have best practices. Like you don't want the code to repeat. You don't want the user of the library to need to repeat themselves in multiple places. Another common example would be like JSON serialization, deserialization. Previous talks on static reflection talked about SERD. And yeah, so if you want to, you take a raw JSON string and you want to deserialize it into a struct, that also requires some amount of reflection. Some optimizations, like if you guys know from like CS 2106 operating system plus or like 2100, you know there's a cache, right? And if you access things sequentially in the cache, it's a lot better than like jumping around in addresses. And so when you have an array of structs, generally the access pattern is not so optimized. But if a struct of arrays, on the other hand, it's a lot better. So when we code, it's nice to have an array of structs, but for performance, it's best to have a struct of arrays, and reflection can help you do that kind of translation from array of structs to struct of arrays. So before C++26, there was a bit of runtime type information that you could have. Namely, type ID gave you some kind of mangled types, which I think depends on the compiler if I'm not wrong, but that does give you some type information. And dynamic cast also kind of helps you check whether something can be casted, in contrast to static cast, which just gives you undefined behavior if you cast it wrongly. And this was quite limited in functionality. But with C++26, there's many proposals to include reflection, and the main one is the first one, P2996R13. R is the revision. And it's basically that's the bulk of it, and the rest are kind of like supporting the first proposal. So I'll go through like maybe I think 2 or 3 of this, mainly the first one. So if you go to the first one, by the way, later I'll send the slides, and these are all clickable links. So yeah, if you go through the first one, you'll see that there's a lot of examples that they list, and I'll be going through those examples one by one. So I stole this picture from Tim Song's C++ Meetup 2 slides. Who was there, by the way? Anyone was there? Okay, nice. Yeah, you guys should go for like the upcoming meetups. I think there's one coming to NUS actually in like March something. So P2996 introduces reflection via a single what we call reflection type called std meta info. There will hold information about reflection, and roughly speaking, the way you do reflection in P2996R13, okay, I'll just call it C++26 from now on. But how you do reflection here is you use something called a reflection operator, which is also called a unibrow operator. I'll show you later. But it helps you convert like source code into a std meta info, and then you manipulate the std meta info as if it's just a normal type, like as if it's just a value. And this is all done at compile time, by the way. And then you convert back from a std meta info into source code using what we call the splicing operator. So before I talk about the examples, if you want to try it out yourself, Godboat has a Clang P2996. It's one of the compilers. It's an experimental compiler. And there's also some others, like EDG has one also. I'm not sure if GCC has, but you can go to Godboat. That's the easiest way to set it up. But if you want a bit more AI support, like using Cursor, then you can git clone this. That's what I did. I git clone this repo, and then I set it up locally. And you can just tell, it's quite a pain to set up, like, and you don't really get much value out of it. So you can just tell Cursor to like to set it up for you, which works quite well. And in the end, basically, when I run my experiments, it ends up looking at something like this command, which is quite long, but all it does is it turns out you need to compile the libc++ in this Clang P296 compiler as well. And you need to compile like the standard library using this compiler. So it's a little bit annoying, but AI can help quite a lot. Yeah, so without further ado, let's go into the few features of 2996. And yeah, I'll be going through most of these one by one with examples. Yeah, so from the very start, there's something called a splicing operator, which is like the caret. And some people call it a unibrow operator. I don't think that's an official name. And basically what that does is it helps you look at the first example over here, it helps you convert some source code, like for example, in this case is int, and it helps you convert it into a std meta info. So the R over here is of type std meta info, and if you want to convert it back into source code, you use a splicing operator, putting in a std meta info, and then you get like source code. You need a type name over here if it's ambiguous whether it's whether it's a type or not. You can always put type name, like it doesn't hurt, it just hints to the compiler that this is a type. And to prove to you that it's a std meta info, you can do this trick where you do this, you could create this templated incomplete type, and basically, because type ID R doesn't seem to work when I tried it, you can do this thing called this template trick, and then the compiler will not compile, but in the compiler error message, you'll see like the type of it, which is const meta info. So this is like a way to print your type using the compiler, kind of like using the compiler like an interpreter. Yeah. So this is a useful debugging trick. So yeah, back to this. So if we look at the code over here, it's a minimal example of how you can access members. Yeah, access the members of S. Yeah, using this member number function. So maybe the question is, how do you not hard code like the bunch of conditionals over here? So that brings us to our second feature, which is non-static data members of. So this is something that acts on std meta info. As you can see that this method acts on this function acts on the _s, and then you pass in the context as well. More on that later. But this should give you like something like a vector of std meta info. Yeah, and then you can index it using the n, right? And then if you try to access something that's out of bounds like 5, then you get a compile error. So all of this happens at compile time. And so what is the context over here? The context over here is called the access context, and basically it helps you settle things like scoping. So if you put unchecked, then your static reflection code can access private fields, which may not be what you want. So most of the time we want to use current, which is just like the default rules of C++ access. I have a small example here illustrating the difference between the two. Okay, and that brings us to our next feature. So identifier of is something that can get basically the name of the field. So just now we access it using index number, but in this case, what if we want to access it using like a name, right? So I pass in, I call this member named with J inside as a string, and then it will look through each member one by one. So you see that the non-static data members of, it returns you a vector, and it returns you a vector of meta info, and you can iterate through the vector just like how you iterate through a vector of like an integer, right? So you can iterate through it and you can do comparisons, and this entire thing happens at compile time, so you must mark the function as const eval. There's some fancy rules with like what is const eval and what is not. Yeah. By the way, if you guys have any question at any point, just shout it out. It's chill. Yeah. So in this case, we're going through each field. Oh yeah, question.
Sorry, this is like just from previous. What makes this like hard to? What makes this like easier to do in interpreters and harder to implement in compilers?
In terms of, are you referring to like in terms of difficulty of implementing this like reflection?
No, you just mentioned earlier that like reflection is like harder in compilers.
Right. Okay, I'll say that when you interpret reflection in when you implement reflection in interpreters, because your interpreter usually has like a handle to the entire object, and then all the fields of the object are just like strings in the interpreter. You can very easily like tell the interpreter to just return you the raw data that makes up the object at runtime, right? So interpreters it's very easy to implement runtime reflection. Whereas I claim that it's very difficult to implement runtime reflection in a compiled language, right? Does that make sense? This is what I think. Like, it's very difficult to implement a runtime reflection in a compiled language because when you compile something, you lose like a lot of information about the original source code. So I guess the next best option would be to implement compile time reflection in compiled languages, and yeah, I guess the main claim I wanted to make was that it's very difficult to implement runtime reflection in compiled languages. Yeah, and that's why we resort to compile time stuff. Thanks for the question. Yeah. Any other questions? Okay, great. Thanks. So yeah, so this code just look through the different data members of this S, and then if it matches the thing that we're looking for, then we return that field, and realize that field is of type stud meta info, and then that's why over here we need to splice it back. So yeah, so before so bring us to our next example. Before 2996, whenever we wanted to convert like a list of types into a list of sizes of those types, right? We need to do some fancy like meta programming with veridic templates. It's very, very ugly and verbose. But now with 2996, you can treat the vector of meta info just like an ordinary vector, and it can work with your standard like range stuff in C++ as well. So you can just apply transform on it, and then you get this very nice like functional style code. And yeah, small note, which is the size of ... gets the size of the tuple. There's also a standard tuple size, which I was made aware after I write the code. So yeah. So I'll spend a bit of time talking about template meta programming, because I think static reflection can change quite a lot about how we do template meta programming. So I'll go through a brief history also about TMP. So in C++ 11, the tuple was introduced, and I think a question I asked myself was, why do we need to introduce tuple at all, right? Like a tuple can hold like a bunch of heterogeneous types, which just means different types, and a struct can do that just as well. And a struct is named as well, so you can it's even better because you get like neater code, I guess. So why do we need a tuple? Yeah, so anyone wants to hazard a guess? Okay, so the answer turns out to be, in my opinion, the answer is that tuple was introduced because we introduced parameter packs. This is just my own way to motivate tuple. Yeah, I didn't speak to anyone in the committee or anything, but I feel like it made more sense if we think about it from the perspective of parameter packs. So when we write generic code, you know, when you write like in Python you can put like print, and then you can put like any number of parameters, and Python can just use it. So code like that is clearly useful to be able to write. Yeah, this is just very clearly a useful use case of this. Clearly helps like generic programming, right? You can write one function and then you can accept any number of parameters. And so C++ introduced parameter pack to handle that, and that's a ... feature, right? And if you want to pass around this entire parameter pack, it's very troublesome, because everywhere you have the parameter pack, you need to like do the ... and the syntax is really ugly, very hard to read. So the tuple was a nice way to package this entire parameter pack into a single type at compile time, right? All of this is a compile time. And so we can call that like reified or like bundled parameter pack. And later on, C++ 17 introduced stud apply, which helps you unbundle this as well. So this is code with stud tuple, and you can see that in this case, in C++ 11 they also introduced like stud async, which kind of works well with parameter packs, because if you have an async function, chances are that you want to apply it later, and this deferred application of this function, you want to apply the parameters to the function later, and so you need to kind of like forward the parameter pack. And with stud tuple, you can do it nicely by just taking in the parameters, bundling into a tuple, and then later on unbundle it. And that's what, and if you pass a stud tuple through a lambda capture, yeah, it's just quite neat. This is in contrast with if you did it without a tuple, then you need to pass in veridic number of parameters into the capture, which is a lot more verbose and ugly. So yeah, so now we introduce tuple. tuple is useful, great. But how do we print a tuple, right? If you have a tuple, it might be useful to debug with the tuple and you want to print it out. And so there's some minimal code in C++11 that helps you print a tuple. And basically, for those who have taken like functional programming class, you know that if you want to print a list, what do? You print the first guy, and then you recursively print the next part of the list, right? So all of that is basically transferred over to template metaprogramming, just that everything is templated instead. So there's a saying like there's 3 Turing complete languages in C++, right? Macros, templates, and then the original source code. So a lot of like machinery that was invented for template metaprogramming, all the veridic stuff, those techniques, before like template metaprogramming becomes mature, you kind of need to apply these basic functional programming ideas to work with template metaprogramming. So if you want to print a tuple, you kind of need to do it recursively in the templates. And this also means that with recursion, there's a stack overflow, right? Just as a stack overflow in the compiler. So when I tried it out, the limit was 1024. You cannot create a tuple size. You cannot print a tuple of greater than 1024 with this source code. And I think this is compiler dependent, but old compilers also did this very inefficiently. So yeah, so this was with C++11. So with C++14, they introduced something called integer sequence. I think this is one of the, I think C++14 didn't introduce a lot of features, but they did introduce index sequence and integer sequence, basically representing a compile time list of numbers, right? And this did help template metaprogramming quite a lot. So so instead of trying to do things like, instead of trying to do things recursively, print the tuple recursively, now you can let the function take in what we call an index sequence, which is just a bunch of numbers, which is a compile time list of numbers, and now you can unpack that compile time list of numbers to index your tuple. And we apply this trick with initializer list. Usually initializer list is when you have a curly brackets, and then you have like items separated by commas inside it. And usually it's used in uniform initialization when you want to avoid like narrowing conversions in object-oriented programming. But using this trick, we can effectively do a fold expression, which is something I'll talk about later. But you can effectively do a fold expression because if you define an initializer list and you pass in veridic templates, veridic like arguments, the initializer list will take in a list of expressions, right? And it turns out this expression that we're passing in is something that has side effects. So like usually if you define an initializer list of like integers, you usually expect that the integers are just like the expressions are just like numbers, right? With no side effects. But in this case, we are actually passing in so-called numbers, number expressions, which evaluate to a number, but these expressions have side effects, and the side effect is printing out a number. So it's quite funny that like this trick is used in this way. And you also use the comma operator here so that you can essentially avoid, because cout doesn't return anything, so you end up putting just a 0 here at the end of the after printing it out, so this essentially constructs a list of zeros, but the construction of this list of zeros has a side effect of printing out the tuple. So yeah, so this is clearly very hacky, but it was replaced later on with more modern features. So what is this integer sequence? It's a compile time list of integers. Instead of putting in, you can put like other integral types like size t, unsigned, long, and basically you have a compile time list of integers. You can even do like bubble sort on it as well, even though that's not very useful, but it's a fun exercise, I guess. Just to show that template metaprogramming is very powerful and kind of like Turing complete. So yeah, so I introduced this because I want to talk about how compilers make integer sequence effectively, and modern compilers use intrinsics. So to implement this inefficiently, you can do it in old versions of C++. But if you want in modern compilers, they don't want to do it inefficiently. They use intrinsics, which is not great because like now your standard library function depends on the compiler for like help, right? Essentially means your language is not like powerful enough. So with 2996, with C++26, we have this thing called substitute, and this is the example in the proposal. And essentially, this constructs a compile time list of integer. So we can see that we see that this type make integer sequence. It calls this make integer sequence refl, and basically what this does is a constant eval function, which means it runs at compile time, and it takes in it constructs a vector of, let's see, it constructs a vector of, so t in this case is a type, and n is the number of integers you want in this list, in this integer sequence. And you can see that we have a vector of type t, and essentially, so this is a vector of std meta info, right? Sorry, it's not explicit, but this is actually a vector of std meta info called args, and then we are going through this for loop and pushing 0, 1, 2, 3, 4 all the way to n-1 in it, and then at the end we do this thing we call substitute, and we call substitute on integer sequence passing in the arguments. So this essentially creates the type, the templated type. This essentially like does template substitution for you, where it substitutes the args, which is like 0, 1, 2, 3, 4, into the integer sequence. So yeah, the integer sequence is a templated type that takes in the type t, which is what we constructed args with, and then it takes in the bunch of numbers. So you can see that with this is how you implement make integer sequence in 26. And yeah, and so now this is like within the language itself, meaning that we do not rely on compiler intrinsics anymore, which is great. So the next feature would be extract. So when we reflect something, when we reflect a piece of code, it can be a type, it can be a variable as well, it can be a lot of things. And sometimes the std meta info might actually contain a value, right? A value of a variable, and you can extract it using std meta extract. And this is if you try to extract something. If you try to extract a value from, let's say, something that doesn't have a value, like something like a type, then it's ill-formed. So yeah, this is another thing. A very useful feature which essentially lets you write code in this case. So the struct of arrays example uses define aggregate, and this primitive is very useful because it essentially allows you to define classes at compile time. So in this example, we're implementing tuple. So if you have seen the implementation of tuple before, it's very, very large and it's very unsightly. But with C++26, you can now use define aggregate to make to implement tuple really easily. Of course, this is just a snippet of it, but this is like the key idea, that now we can define an incomplete type called struct storage, and then now you can have a const eval block where you call define aggregate on the storage, and you pass in a vector of std meta info. So this tells the compiler to say, hey, take the name storage is a type, right? And currently it's an incomplete type. Now I want you to populate this incomplete type with data members, and data members come from this vector of meta info. So you can programmatically control what goes into this vector of meta info. So you can programmatically control the fields of this struct, right? And basically you can create fields. Create fields of a struct programmatically using define aggregate, and that's pretty powerful, right? So now you can like rearrange structs in. You can imagine how powerful this is, and yeah. So that brings us to that's roughly the list of features that are useful in P2996 to R13, and there's a company proposal called expansion statements. So revisiting our example of how we can print a tuple in in C++ 14. This is how it looks like using the initializer list trick as mentioned just now. And in C++ 17, they introduced to apply. So now you do not need to use the initializer list trick anymore. And now you can, you can use to apply, and it helps you unpack the tuple. And C++ 17 also introduced something called fold expressions. So it allows you to kind of, fold a parameter pack into a single quantity. Those who are familiar with like function programming, there's a concept called accumulate, right? Accumulate, where you accumulate a list, and then maybe let's say you want to accumulate it using a sum. Then you take the list and then it collapses it down. So fold expressions are kind of like accumulate in function programming. So you see a lot of like, for those who say like function programming is not useful in the real world and all that, but is useful in the real world, I guess. Yeah. So so there's a few fold expressions, and this allows you to avoid the gory trick where you use initializer list. And so now this is what printing a tuple looks like in C++ 17. You can see that as we introduce more and more language features, it gets less and less ugly. And arguably this is still like a little bit ugly because it's kind of like functional style, right? Like std apply is kind of like you're applying on, you're unpacking it, and it's still not very clear what's going on from the get-go here, at least at the first glance. So with C++ 26, there's a thing called template for, which is kind of like compile time for loops. So this helps you avoid using std apply. And if you look at this example over here, okay, it's a bit small. Let me see if I can. Oh, actually, it's not that small. Yeah, it's just small on my screen. So over here we have when we pass in a tuple with a parameter pack ts, we call make index reflections on the size of that tuple, and that returns a vector of stud. That returns a static array, and a static array is basically a list of numbers. So make index reflection basically just takes in a number n and returns you a static array of 0, 1, 2, 3, 4 all the way to n minus 1. So basically make index reflection is just returning you a list of numbers, a list of indices. And then now you can go through each one using a template for. So now the capital I in this case goes from 0, 1, 2, 3, 4 all the way to n minus 1. And for each one, you want to call a get of the index I on the tuple. So you can see that now like we can write imperative code. We can write like imperative programming style code using templates, right, and compile time. So that's quite lit. Yeah, so a bit more on this. Template for kind of needs to be supported by this other feature called define static array. So define static array is another proposal that basically the story is this: like when you try to have template for, when you try to introduce template for, compiler authors need to support non-transient const expr allocation, and unfortunately, I guess there's some technical challenges around there. So they define static array to sidestep this by kind of like hinting to the compiler that this is a static array. So yeah. So it turns out define static array and string and object were actually part of the revision 7. Before revision 7, they were actually part of the 2996 proposal, but after that they put it out. I'm not very sure why. So if anyone's have any idea next time or now, or anyone online can just leave a comment. Yeah. So with that, I've introduced a lot of the features of compile time reflection, and there's some project ideas that you can achieve with this. And like, I'm of the opinion that like this is still like a very, I think this is still a very like young, like not a very mature feature yet, and it'll probably take a few years to mature. So like I feel if you want to be the library author of some great library that's used by everyone in the future, I feel like this is a great time to get into it. So I've been trying to write an ORM. For using static reflection, and I think one important thing is to, if you write a library with this static reflection, one important thing is to make sure that it supports existing reflection systems. So like in my case, my ORM, I try to support Boost PFR, which is another one I'm going to talk about soon. But I think it's important to support like existing reflection systems so that people will start integrating your library into their code, right? And then when a new compiler comes out, they can easily like just do a switch. So yeah, I think this is quite a cool opportunity. Besides the ORM, I think like XML parser, JSON parser, I think there are already some works, like some of the C++ community people, like people giving talks and all that, they are trying to have like experimental projects where they integrate static reflection into existing JSON libraries. So like maybe JSON is a bit of a dead end because everyone uses existing libraries already, and then if they're already working on porting it, then like there's not much pie there, right? But I think stuff like ORM is still, I don't think anyone has, if anyone has like a good ORM to recommend, please recommend me, because I want to use like C++ for my own personal projects which need a database, and then like there's no good C++ ORM, so I literally have no choice but to write my own one, right? So yeah. So yeah. So now I'll move on to reflection in other libraries. So there are three that I listed. There's probably a few more, but I think I'll just talk about these three because I think they are the main ones, especially Boost. Boost is very popular. So there's this guy who created this meta programming library. But I think the annoying thing is that it's basically just a tool, but it doesn't really solve the code duplication issue, because fundamentally you want to say like I have a struct, and then I have some way to, let's say, serialize that struct, and then let's say I add a new field to the struct. Ideally, if you add a new field to the struct, you just need to edit at one place. You don't need to edit at like another place, right? You don't want to like need to edit two places at once, because that could introduce bugs. So this guy, he created this library that you still need to introduce the new field at two places, which I'm sure he made people's life easier, but like it still doesn't solve the core issue, which is that the code doesn't have reflection features. So yeah, Boost PFR Boost PFR supports basically tuple type like indexing on structs. So I can have a struct person with a bunch of fields, and usually I cannot get the fields using an index, right? I must get the fields using the name, right? The name of the field. But Boost PFR allows you to use an index, which I guess is quite nice because you can write some compile time code that like generates a list of indices, like make index sequence, and then you can go through all the fields of a struct, which is nice. But I was very curious how they do this. So it turns out if you dive into the source code, they only let you get up to index 200. So yeah, so it's hard coded. Like they just have a whole list of like cases 0 to 200, and it's probably useful for like, it's probably like useful in all practical cases, but like theoretically speaking, it's still ugly, right? Yeah. So like if you want to define like a template meta programming Turing machine, then like you end up having only 200 slots. Then it's like, what's the point, right? So yeah. So that's Boost PFR. There's Boost HANA, which allows you to have reflection over struct fields, data members, but unfortunately you have to use their macro system, which is, the macro system I guess is nice, but it's just not as elegant as supporting static reflection in the main language. I feel like if you, let's say you absolutely needed static reflection in your code today, I'll go with like Boost HANA, because I think it's the neatest. I think it's the neatest way to. It's like the best option we have at the moment, which is use macros to support reflection. But macros are not type safe, right? They're just like string substitutions everywhere. So there's a bit of an itch to scratch here, I guess. But yeah, otherwise HANA is great. I think this would be my go-to option if like static reflection wasn't supported. Yeah. So yeah, we can talk about now we talked about various frameworks. Let's talk about some languages as well. So Rust, there's it turns out that officially speaking, Rust doesn't have static reflection, which is quite surprising because like Rust is a very modern language. They probably thought about it, but I think the Rust community probably decided to go with procedural macros instead, which is something that's actually even more powerful than static reflection, because the procedural macros, they can read the AST and modify the AST directly. So there's like this super cool thing, like if you have ever done like crypto programming, like blockchain programming, a lot of the libraries are in Rust, and then they have they'll let you define like solidity code, like smart contract code, and then they'll have a procedural macro that converts the smart contract code into Rust code. So like it's kind of like a language transpiler almost. At least it lets you create like bindings, right? Then your Rust library can call the smart contract code. So that's insanely powerful. I don't know if static reflection will be able to. Actually, I think it will. So technically, if you have static reflection in C++, I think this was one of the things that Herb Sutter was talking about, was raving on about, that you kind of have a transpiler at hand, right? If you just like do a std embed, you just do like an embed, you embed like entire file of source code in, let's say, some other language into your C++ code, then it's just a giant string, right? And then you can process the giant string by writing your own parser, which runs at compile time. And then you can do anything if you want with the parser, and then now you have like a transpiler kind of. So yeah, I don't think procedural macros is. I take back the claim that procedural macros is more powerful. I think both are equally powerful, but I guess procedural macros is a bit neater because you can directly modify the AST as opposed to like needing to write your own. Yeah, but I'm sure people can build libraries around static reflection as well. So yeah, so anyway, to me, like the claim that Rust doesn't have static reflection is a bit, I feel like it's a bit misleading, because you have reflection at a syntactic level, right? You just not at a semantic level. You just can't say like, oh, this token in the AST is a type. You just don't really have that. So to me, it still kind of has, but that's opinionated. Java is interesting. They introduced introspection since 1997, and there are a few possible mechanisms. You can read about them here. I don't know the details, but there's a very interesting new project called Project Babylon, which actually Java has like a lot of interesting projects ongoing, like Babylon. I think there's one called Valhalla, and there's quite a few like projects that are ongoing. And Babylon is supposedly supposed to be like code reflection, and allows you to and basically with code reflection you can like write transpilers quite easily. And I think one of the goals of Babylon is to make like GPU programming more accessible in Java, which is quite a goal. Yeah. Lastly, in Python and JavaScript, it's a runtime language, so it's quite powerful. It can do a lot of things at runtime, because it's interpreted language, as I mentioned earlier. So yeah, so with that, I've come to the end of my presentation. Yeah, you guys have any questions, feel free to just ask. Yeah. Thank you. Yeah, anyone wants to ask any question about anything really, it doesn't need to be about static reflection. Okay, if not, yeah, I guess you guys can just hang around and talk to each other, and